The goal of this lecture is to prove the first two big theorems of this course, the monotone convergence and the Fatou's lemma. As you probably already seen it from PMATH 450, they are really important theorems for integration. And we're just proving a general version of the version you saw in 450. The proof is really almost the same compared to the Lebesgue integration. So I'll try to go through it fairly quickly. So in this video, I'm going to prove the monotone convergence. So the setup is that suppose I have a measure space, let's call it xa and mu, and suppose I have a sequence of increasing non-negative functions, let's call it fn. Each of them are assumed to be measurable, so we already saw that if you take their limit, well, because it's increasing, the monotone convergence for sequential numbers tells you the limit exists. So you can just let f of x to be its limit. The f of x may take some value infinity at some point, but that doesn't matter. So we can see that f of x is also measurable. So the monotone convergence theorem is telling you the integral of this limit is the limit of the integral. Okay, so you only have a pointwise limit, but you can say the limit of the integral is the integral of the limit. That's for increasing sequence of functions of increasing of non-negative functions, all right? So the proof is really working the same as the one you saw in 450, so I'll try to go through it fairly quickly. So one direction is really easy, so because fn is increasing, you can convince yourself fn is less than or equal to f, or it's just by the limit, okay? So last time we saw that the integral is monotone, so that will mean the integral of these f and d mu is less than or equal to the integral of f d mu. Okay, so I proved each of these integral of fn is bounded above by the left-hand side. Okay, so basically we need to prove the other direction. So we need to kind of decrease the left-hand side by a little bit and show that the integral of fn can be bounded below by that value. Okay, so to do that, let's take any simple function because the integral of f is defined using simple functions. So let's let this simple function is sandwiched between f of x and 0. So this is non-negative. And so I want to compare this integral of fn with the integral of this simple function. Well, the simple function can approximate this f really well, so let's make it slightly smaller. Okay, so let's consider the following function. So let's fix an epsilon greater than 0. And let's just consider this simple function if I scale everything down by 1 minus epsilon. So epsilon is a really small number. If I scale it down, it's still simple. Okay, so this is simple. But now it's going to have a gap between this simple function with f of x. Okay, so what I mean by that, so if I consider any x inside x, if I evaluate this 1 minus epsilon phi of x, okay, so this is strictly less than f of x. Okay, so there will be gap. Okay, so if I draw a picture here, so if 0 is here, then this is 1 minus epsilon psi of x, and it will be strictly less than f of x. Okay, I really need to plug in this 1 minus epsilon to make this strictly inequality, otherwise I only have less than or equal to. And now because these fn of x is converging, so this is fn of x, they are converging, so you can imagine they can be less than this 1 minus epsilon phi, but eventually you will get something bigger. Okay, so for not for all, but for n large enough, you will have that the fn of x is greater than 1 minus epsilon phi of x, okay, because fn is converging to f of x pointwisely. Okay, so now let's consider these set where the fn is actually greater than this phi of x. Okay, so let's consider, let's let an to be all the x so that fn of x is greater than 1 minus epsilon of phi of x, okay? And because phi is a simple function, it only takes finite value, and these fn of x, they are measurable. You can convince yourself this an, first of all, is measurable, okay? And because for n large enough, these fn will always greater than the 1 minus epsilon phi of x. So you also have the union of these an is going to be the entire x. Okay, so for every x in x is eventually in one of these an. Okay, and greater than or equal to 1. And again, because f of x is increasing, you also have that the an plus 1. So if your fn of x is already greater than the right-hand side, then the fn plus 1 will be even bigger. So an plus 1 will contain the an. Okay, so you really have an increasing chain. Okay. So now let's consider the value I of 1 minus epsilon of phi. Okay. So again, this is, last time we showed this is really the integral of this 1 minus epsilon of phi, okay? So this is a simple function, so how about, let's say, phi is equal to summation of alpha I chi of bi, where I going from 1 to n. So this is just by definition, I going from 1 to n of alpha I, and I multiply everything by 1 minus epsilon. I have a mu of bi, okay? Well, because this an is an increasing chain and a union to x, we show that the measure is continuous from below, okay? So you can replace each of these mu of bi is equals to the limit of mu of bi intersect an, where you take n goes to infinity. And because this is a finite combination, so here n is finite, so you can put the limit out, okay? So what you get here, this is essentially the limit when n goes to infinity of this summation n going from 1 to, well, I going from 1 to n, alpha I 1 minus epsilon, and you do mu of bi intersect an, okay? And this one is essentially this function 1 minus epsilon phi multiply the characteristic function of an, okay? And by our choice of these an, so on each of these an, we saw that the fn is at least 1 minus phi of x, okay? So on each of these an, this is less than or equals to the fn of x, well, also chi of an. So on each of these an, fn is greater than 1 minus epsilon phi. Okay, so this one will be less than or equal to, well, let's keep the limit here and goes to infinity, of the integral of these fn of x chi of an d mu, okay? So this, again, is really follows from the integral is monotone. And you can see that this, because you're integrating over a smaller interval, okay? So these fn of x, they are always less than equals to fn of x, okay? The fn chi of an less than equal to fn of x. So each one of them is going to be less than or equals to the integral of fn d mu, okay? And of course, you can keep the limit, okay? So what we get is that I start from I of 1 minus epsilon of phi, so which is 1 minus epsilon of I phi, by the I function is linear. And I show that it's less than or equals to this limit. Okay, so because epsilon now is arbitrary, and I take the supremum of all these simple functions phi, then what I get is 1 minus epsilon on the left-hand side. When I take the sup, it will give me the integral of f d mu, and it will be less than or equals to the limit on the right-hand side. Okay, so the integral of fn d mu, Oops, I don't know why it's auto-correcting me. All right, so this basically shows the other direction, so I can let epsilon goes to 0. We finish the other direction. Okay, so this is the end of the proof.